Hello, good evening, everyone.
Good evening, ma'am. Good evening.
Yeah. All right. So today we are going to start week 12. So this is last. Uh, so there will be one more session for week 12. We will do the problems. Today we'll stick to the theory of week 12. Did anyone go through the lectures?
Yes, ma'am.
Hmm. So week 12 deadline is 18th of December, right?
18th of December.
Okay. All right. So we'll start with so in week 12 we have only two topics. So one is the classification loss function. So the first topic that we have is classification loss function. So we are going to look at all the classification algorithm, and we are going to see what kind of losses we have used for those algorithm. And the next is like we are going to see a very small introduction on the neural network, which is like a very short intro to this topic. Like in more detail we'll be seeing in when you go to the higher courses. So classification loss function and the neural network. Okay, so let's start with the classification loss function first. All right. So, what have we seen in any classification problem? So, we had the data set something like, okay, huh. So we had a data set which was like your x1, y1, x2, y2. So on, let's say you have n data set, right? And here, each of the xi, we had taken that it belongs to some RD, and my yi's, the labels, were plus one, plus minus one, right? This is what we had seen. Now, for any classification problem, what we wanted to learn is some function h, like a model h or a classifier h, which maps from RD to some plus minus one. Right. This is what we wanted to learn in the classification problem. Now to check like how do we check like any model that we learn on this data set, how do we check its performance, right? How well it is performing. So for that we know that the natural way to or more intuitive way to deal with certain kind of these kind of problems is like to check its error, like how is the error in case of like if it's a regression problem, like we have also seen the loss function classification, we can still do the same thing. So to check the performance of this function that we have achieved at this edge, we are going to look at the error. So the error, how do we define this error? So the error, we defined it as some indicator function. So we are denoting it as something like, or maybe I also we can denote. This is the indicator function. And we are saying indicator of h of xi not equal to yi, right? And I is varying from 1 to n. So this is how we define this function, this error function. And how do you define this? How can, this is nothing but your indicator function, right? So any indicator function, if you see, so it's more like, so if this is, let's say I want to check. So in this case, the x is your h of xi not equal to yi. So how can you define it like this? So indicator of x means uh, if if whatever is there inside this function is true, we are going to give it as 1. Otherwise, we are going to give it as 0. So if x is true, we give it as 1. And if x is not true, we give it as 0. So for this case, for a classification example, what we are going to say is, in case my true label is not equal to my h of xi, I am going to give it a value 1. Otherwise, it is 0. So all the number of mistakes that the model is making, that is what my error function is giving here. So, but what we also said is, like, where are these h we are going to look for? Like, if we try to, like, if we go to a certain extent and try to make this training error as 0, then there is a high chance that we are overfitting the model. We had seen that, right? So to avoid that, like, we can restrict to a linear space, so that we denote it as h of linear. And what we said is that we will minimize this error. So we'll minimize this error of h of xi not equal to yi, right, over the space where h should belongs to h linear. So we are only going to see the we are only going to see the h which belong to this h linear, right? Now we are minimizing it over what? We are minimizing it over some w which belong to rd. This we know. Now what we can also do is, sorry, this is I is from 1 to n, and here h linear, right? So now we are looking at only this space of function, which is h linear. Now, how do we define this? How do we define this h of x? We know that this h of x can be defined as w trans set of all x, such that you have h is equal to w transpose x, w transpose xi, right? So this can be equivalently written as minimize your indicator function. And in case of the classification problem, the way we had defined our h was h as, we are going to look at sign of w transpose xi, right? Sign of w transpose xi, and we are going to see whether this is equal to yi or not. In I is varying from 1 to n, and this is w belonging to rd. Right? But in case we also add a bias term here, so this can also be written as, not equivalently, but in case we have a bias term, we can write this as minimize w belong to rd, b is some real number, and indicator of sum over indicator of. Now, instead of looking at sign of w transpose xi, we are going to look at sign of w transpose xi plus b now, right? So we are going to look at sign of w transpose xi plus b, and we are going to see whether this is equal to wi or not. So this is one way to define your loss function or error function. And we want to minimize this function. We want to minimize this objective, basically. So we knew that, like, we had not seen like why this is an NP hard problem. It is beyond this, like, we cannot prove this in this course. But what we had seen this, like, these kind of problems are NP-hard problems. It means you cannot solve it in some polynomial time. So to deal with this, like how do we, since it's an NP-hard problem, how can we deal with this, right? So now we are going to see this loss in a different perspective of this loss function. So the one view that we are going to look at is the regression view. So when we are saying the regression view, means like you're going to use this regression, like whatever loss you had used in the regression problem, can you use that for this classification problem? Then, since we had also seen various classification, various learning algorithm for the classification technique, so we are going to look at like how the losses differs in all those techniques. So what are the classification algorithm we had seen? We had seen Perceptron. We had seen our SVM, soft margin, hard margin, SVM we had seen. Then we had also seen the logistic regression. So this also we are going to look at. And of course, decision tree and so on. So in this week, we are going to look at, first we'll look at how can you view this classification problem, which is an NP-hard problem. How can you view this as from the regression perspective? Next, we'll look at the SPM and the logistic regression, and then we'll go to Perceptron, and then we'll move to boosting also. So Perceptron, uh, okay, boosting not much. We are only going to see like what loss we have used. We are not going to see in detail. So specifically these four. All right. So okay. So like if we look at any single data point, let's say I have some X and some Y. All right. Then in that case, what we are trying to do is we want this like we have some edge which is mapping from plus RD to plus minus 1. And the way we have defined our loss function, that is indicator of h of x not equal to y, right? This is how the loss function is defined. And this we are going to talk about for just from the perspective of just one single point. So we have taken one single point, which is x comma y, and the indicator of indicator function of hx not equal to y. So what can we write this as? So we had seen that hx can be written as, so for the classification, h of x is sine of w transpose x, right? This is what we know. So this can be equivalently, you can write this as h of x as sine of w transpose x not equal to y. And this can be, so sine of w transpose x not equal to y. And this term inside, right? So this you can write it as indicator of w transpose x times y is also less than 0. Okay. So why is this why is this true? So see, you can think of it as like maybe here. So you have w transpose x and then you have y, right? And then if we are going to look at this, so if sine of w transpose x, if sine of w transpose x is greater than 0, so sine, if the sign is greater than 0, and if the label, the true label is, let's say, plus 1, then in that case, my sine of w transpose x times y is also greater, is going to be greater than 0, right? So if I take the product, which is sine of w transpose x times y, so this is going to be greater than 0, right? And in case the sign is less than 0, then my y should be, the true label should be -1. But in that case, again, I can get this product to be greater than 0. So in these two cases, this indicator function is going to give me the value 0. Otherwise, it's going to give me the value 1, right? So in case this is greater than 0 and this is -1, then I know the product is 0. And in case the sign of W transpose X is uh, uh, less than 0 and the true label is +1, then again I know this is going to give me less than 0. So so we can write this loss function, this indicator of fx not equal to y, as this. So like how does this loss function look like if we plot it? So if I think of it as, so now let's take my W transpose X to be some g of x, or we can take, yeah, this is fine. So let's think of it as g of x times y. Okay. And this is my loss. So we'll plot like how does this gx times y vary with respect to like how does the loss vary with respect to this value, right? So if this is we know that if this is less than 0, so if my W transpose X times Y is less than 0, then my indicator is going to give me +1. And otherwise, and if my g of x times y is greater than 0, it is going to give me value 1, value 0, right? So for W transpose X times Y to be less than 0, that is g of x times Y less than 0, I am going to always get 1. That is what this indicator function is saying. Now, if I take any, if my g of x times y, if this is greater than 0, then I'm going to get the value 0. So this is how the loss function, the 0, 1 loss function is going to look like, right? And I can see that this is a discontinuous function. This is not differentiable. So so what can we do to get certain losses which can be used as an approximation for the 0, 1 loss? Since we know this is an NP-hard problem, and as we can see from here also, this is not also a convex function, right? So now we want to find some approximation of this loss which can be used to deal with this NP hardness of this classification problem, right? So the first way that we are going to look at it is through regression. The very first algorithm that we're going to look at is regression. So can we use this regression loss to solve this classification problem? So if you remember
Hello,
in
ma'am.
yes,
Ma'am, how this loss we got, ma'am? It's one and then zero. How can you explain once?
this graph,
Yes, the
right?
loss.
Hmm.
Yes, yes.
Um,
Uh, what we are taking, the loss is what in from
hmm.
sign of W transpose
this
X.
this this is your loss, right? I mean, this is your
Okay,
loss, right? So how do you define
okay,
the indicator function? Like if anything inside this indicator function is true, right? If anything inside this indicator function is true, I am going to say this will be 1. The value will be 1. So in this case, if I'm saying anything inside this indicator function, so in this case, it is if W transpose X times Y is less than 0. Okay. So this W transpose X times Y is less than 0. If it holds, then we are going to say it will take the value 1. Okay. and we are plotting the graph of g of the loss versus g of x times y, and g of x we are taking it as w transpose x.
Okay, got it. According to the sign, W transpose of X times Y, if this condition satisfies, it will be
Hmm.
one,
Ha, yeah,
else zero.
L0. So,
Okay, fine.
so now basically here you are seeing W transpose X times Y. So now if W transpose XY times Y, I know if it is less than 0, I am going to give it the value 1. So anything here, like beyond 0 on the left side, I am going to give it a value 1. So that is why you see this 1, like for every W transpose XY less than 0, you have 1. And anything where W transpose XY is greater than 0, you are going to get 0. That's how indicator function is defined, right?
Got it.
Hmm. Okay. So now, all right. So we'll see like the very first algorithm that we are going to see is the regression problem. So if you remember, like in regression, the loss that we had used for regression was the squared loss, right? So if you if you have to take, let's say if H is your model, and you have, let's say it for one data point which we had talked about, let's say for talk for XY. So if you had let's say this point, this data point x comma y, and H was your function, the loss of this function can you can define it as H of x minus y a whole square. Right? This is for single point, but if you had more than one point, we could have taken like summation over I varying from 1 to n, right? Summation over this. But since we're talking about just one point, so we can we'll go ahead with this. So this is the loss that we have defined. So let's stick to RG. So what we are saying is, since this is a classification problem, my H, we are going to define it as sine of gx. Okay, sine of gx. This is how we are defining my H as. So if I take, and what is this g of x, as we had said, it is just W transpose x in case it is a linearly separable. I mean, for the linear, if you're looking at the linear functions. Uh, Now, if you look at the loss of g for the data point x comma y, this is going. What you're going to get here? You are going to get g of x minus y a whole square, right? This is the loss that you will get. But since we are using this regression for this solving this classification problem, I know that this y is not belonging to a real number. Here y belongs to this plus minus 1. All right. So what we are saying here, that this gx minus y whole square, since my y only belongs to plus minus 1, so this can also be written as g of x minus g of x times y minus 1 whole square. So somehow we are trying to bring this gx minus y whole square to gx times y, because when we had plotted the 0 1 loss for the classification problem, like we were plotting the loss, plotting the graph for loss versus gx times y, right? So we'll try to come to the this common notation. So that's why we are saying that let's write gx minus y as gx y minus 1 whole square. We'll see why this is also like they both are equivalent. So if we solve for gx minus y whole square, what should we get? We'll get gx square plus y square minus 2 gxy, right? And this is since y belongs to only plus minus 1, this can be written as gx square plus 1 minus 2 gxy. Okay, but now let's see why this can also be written as g of x times y minus 1 ka whole square. All right, so this can be written as gx square y square, which is going to be just 1, plus 1 minus 2 gx y, right? So you can see that they both are equivalent, they both are same. So since now we saw that this gx minus y whole square can be written as gx times y minus 1 whole square, we will now plot the loss of this regression problem and see how it is varying for our 0, 1 loss that we have seen. So, okay. So the loss that we had seen for, again, we can plot for gx times y, and this is my loss. So this was our original loss. This is my 0, 1 loss. Okay. Now for this problem, right, we are saying that this loss can be written as gxy minus 1 whole square. Okay. So since this is gx times y, and let's say we have 1 somewhere here. So if we take gx times y minus 1 whole square, you're going to get a parabola, right? An upward facing parabola, which is centered at 1. So you will have some parabola over here. Okay. So what we are seeing here is, so actually it will be at 1. Okay. So this is this loss is gx y minus 1 whole square, and this is my original 0, 1 loss. So this loss, we can call it as also regression loss or squared loss. So for this loss, like this 0, 1 loss, what we are able to see that we have now approximated it using this regression loss, right? So like here, since this is a convex function, you can see that this squared loss is a convex function. It is some convex approximation of our original loss, but it is not approximating it in a good way, right? It is a very bad way to approximate our 0, 1 loss, because like if we see that anything, any gx times y, if it goes greater than 1, my like the loss should be ideally 0, but if I use this regression loss, I can see that it exponentially increases, right, with the increase in gx times y value. So although this, this is able to approximate, and this is a convex function, we can get a global minima, but this is not a good way to approximate this problem. So we'll see, like, if this is not a good way to approximate this regression loss, is not really ideal for solving this NP hardness of the classification problem. So we can see, like, what are the techniques do we have, what are the losses that we have that can be used as an approximation for this problem. Okay. So now we will go ahead and see some different classification techniques and see whether those can be used to approximate these losses. All right. So the classification, the very first classification technique that we will see is So soft margin SVM.
Ma'am, in the above problem, like we are not
Hmm.
able to fit those convex in 0, 1 loss.
Yeah, we are not able to fit this in the 0, 1 loss, because you can see like both are like both these graphs are very different, no? Like this is your 0, 1 loss, which is discontinuous, and I know this cannot be solved. It is not even convex. But we try to approximate. We try to use this regression loss for approximating this, but it is not doing the job that we were expecting in a way, right? Because anything beyond 1, you are going to like it should have given the value 0, but it is going to increase exponentially, right? It is squaring the loss. It's increasing beyond 1, so it is not a good way to approximate this loss.
Okay, ma'am, fine.
Yeah, because anything beyond this will make a very large error, which is not we want. So we'll now see what can be done from to get rid of this. So
Ma'am,
hmm, hmm,
this we
yes,
are doing to get rid of NP hardness of
NP
that
hardness of the classification
original
term,
problem.
binary classification loss. Yeah.
Okay.
Okay. So so one algorithm that we had seen for this classification technique is SPM. So more specifically, we are going to talk about the soft margin SPM here. So what was the what was the objective for the soft margin SVM? So the problem looked something like this. So we wanted to minimize our norm of W square time divided by 2 plus some constant, some hyperparameter, and sum over epsilon I. This is what we wanted to minimize. And we wanted to minimize over W and epsilon. Um, okay. And what were the constraint we have? The constraint we had was my W transpose Xi times Yi plus epsilon should be greater than equal to 1, right? And this epsilon I should also be greater than equal to 0, right? These were the constraint, like the right that data point pays to go to the right side should always be greater than 0. So these are constraints that we had for the soft margin SVM. Now, if we try to write it in a little different way, so what can be done is we can write the constraint a little differently. So what can be write this as? This can be also written as that my epsilon I should be greater than equal to 1 minus W transpose Xi times phi I, right? And the second is that my epsilon I is greater than equal to 0. Right? So now using these two, so the first is that my epsilon I should be greater than equal to this term, which is, let's say, 1 minus W transpose Xi Yi. And I'm saying that my epsilon I should also be greater than equal to 0. Okay. So let's say this is the situation that my 0 is lesser than 1 minus W transpose Xi times Yi. So both should hold. What we are saying is that my epsilon I should be greater than equal to this, and my epsilon I should also be greater than equal to this. So what is common in this? What is common in this is this reason. So I can just say epsilon I should be greater than equal to 1 minus W transpose Xi times Yi. This is the case when my 0 is lesser than this, right? But what will happen if you have 1 minus W transpose Xi Yi is lesser than 0? So in this case, what we are saying is that my epsilon I should be greater than this term. So my epsilon I is greater than this term, and my epsilon I should also be greater than 0. So in this case, we are going to go with that my epsilon I is greater than equal to 0, because both should satisfy. And here we are going to go with that my epsilon I is greater than equal to 1 minus W transpose Xi times Yi, right? So if we have to combine it and write, then we can write these two as, so whatever is maximum. Yes, yes, so they
Ma'am, why we are trying to interchange these conditions? What we are trying to get?
we are not trying to interchange. So we are not trying to interchange anything. We
So
are just
one,
see, we had this. This is what we had seen, right? This was the formulation for the soft margin SVM. We know that, right? So, but in the constraint, you have this. The one constraint is epsilon I greater than equal to 0, and the other constraint is this one. So, if some way if we can also just write epsilon I to be this, right? So now what we are saying is that my goal was to minimize this objective, and what my objective should also consider is that my epsilon I should be both greater than equal to 0, or it should be greater than equal to 1 minus W transpose Xi times Yi. It should satisfy both the constraint, right? So we saw here that if one whichever is greater, like whether 0 is greater or 1 minus W transpose Xi times Yi is greater, whatever is greater, we are going to go with that constraint, right? We are going to put that as the bound for my epsilon I. So looking at both these cases, what we can say is that I can write my epsilon I as it is greater than equal to max of 0 comma 1 minus W transpose Xi times Yi, right? This is combining both. All right. So once we combine both, so what we have here is, now my problem is, now my problem was to minimize this objective, right? Minimize this objective plus C times this epsilon I, right? But this is what we are saying is that this epsilon I should be greater than equal to max of 0 comma 1 minus W transpose Xi Yi, right? So since this is going to get added as some term, so at the optimality, we are going to get epsilon I as just this term, max of 0 comma this. So we can just, in the objective, instead of writing sum over epsilon I, we can just write this as C times what was there in the epsilon I. So in epsilon I, we have max of 0 comma 1 minus W transpose Xi times Yi, where I is varying from 1 to n, right? So in a way, we got rid of this epsilon here, correct? So this term, so what, now my soft margin SVM formulation, which was originally this, we are able to convert this into this problem, all right? So what we call this term as, this is my loss term, this is my loss term, and this is my regularizer. This regularizer we had seen, they were talking about the ridge regression, the lasso regression, and so on. So in this case, this is my regularizer term, and so if this is my loss, term, right, which is C times max of 0 comma 1 minus W transpose Xi Yi. We'll see how this loss can be plotted. Like how does this look like? So if you notice over here, this again, this W transpose xi times yi, which was we were plotting the loss for gx times y, right? And this is nothing but this gx times y, right? So now my losses, which so my losses in this case is max of 0 comma 1 minus gxy. This is for one data point that we're talking about. So if we plot this loss in the same graph, so this is my gx times y, this is my loss, this was my original loss, and the regression loss that we had gotten was something like a quadratic function, right? This was my regression loss, and now we have to look at this loss for the SVM. Okay, so this what this is saying is that this is equal to max of 0 comma 1 minus gx times y. So since this is gx times y and 1 minus gx times y is going to be, so in case your gx times y is greater than 1, so if this is greater than 1, I know that this term is going to be negative, right? Because if gx times y is greater than 1, then 1 minus some bigger term than y, so this is negative. And if I want to take max of 0 comma some negative term, I know I'm going to get 0. So what we are going to get is anything beyond gx gx times y, you have this line, right? You have this line. Now at when gx times y is equal to 1, I'm going to get 0, and when gx times y is equal to 0, I'm going to get 1. So you will get another straight line over here. Okay. This, right? So the curve that you see in this violet color, this is the loss for my SVM, and this loss has a special name, and we call this as hinge loss, right? So this is how the loss looks for my SVM problem. So again, if you look at this loss, this hinge loss, you can see that like this is able to approximate my original 0, 1 loss in a proper way. Like it is also like it is a convex function, and it is in a way like it is a better approximation as what we had gotten for this regression, this regression loss, right? It is doing a better job than what we had seen for the regression loss. Any doubt in so far? Any doubt in the system?
Ma'am, how is it a convex function, ma'am?
How it is a convex function?
Yes,
So,
ma'am.
how do you define your convexity, convex function? So, any point that you take inside this and you draw a line, it should lie inside this region. That's how you do it.
Yes,
One way to
ma'am.
do it. So, any point that you take inside, so you have something like this, no? So, any point you take, and you will see that you can always draw a straight line which will be inside this, right?
Okay. Okay, ma'am.
So this is doing the job of like this is a convex approximation for our 0, 1 loss. And in like what we have also seen is like this is so far the best approximation that you can get for this 0, 1 0, 1 loss. So this was about the SVM. Now, next, what we are going to look at is the logistic regression. So the third algorithm that we will look is the logistic regression. So in logistic regression, what we were trying to do is we um, were trying to maximize the log the likelihood of the likelihood of the function, where the function was with respect to this W, right? And so the problem was to maximize the log likelihood. So how were we writing the log likelihood there? It was some function of W transpose Xi. It is more like a 0, 1, like Bernoulli kind, right? So you can write this as p to the power Xi 1 minus p to the power 1 minus Xi, right? And there in logistic regression, when we're looking at logistic regression, what we had seen is that this can be written as, so the p which I'm writing over here is basically some logistic function of W transpose Xi to the power Zi, okay, and 1 minus, so 1 minus p, so 1 minus sigma of W transpose Xi to the power 1 minus Zi. Okay, so and we were this is with W. We were trying to maximize with respect to W. I is varying from 1 to n. All right, this was our problem. And how was this logistic function defined? This logistic function was defined as, so sigma of A, if you take, that was, this is nothing but 1 upon 1 plus e to the power minus A, right? And so if we solve this problem, which is maximize this log likelihood, maximize this maximize this likelihood, then if we take the log, what can you do? So if you take the log, you have max over W. This product becomes summation, and you will have, when you take the log of this, you will get Zi times log of sigma of W transpose Xi, right? Plus 1 minus Zi of 1 minus sigma of W transpose Xi. Okay, I was varying from 1 to n. But one thing is that when we were looking at the logistic regression, there the Zi's that we had taken was, the Zi's belong to my 0, 1. But since we're talking about here this yi as +1 -1, then we will have to like map this 0, 1 to -1 and 1, right? So what can you write for this? So my what we can say is that if my wi, sorry, if my yi is equal to 1, my zi, I will say I will call it as 1. But if my yi is -1, my zi is 0. Right? This should happen. 1 will stick to 1, but whenever I'm saying my zi is 0, basically my yi should be -1 in that case. Okay. So this is how we can define my zi as. So in short, my zi is equal to 1, 0. So this if yi is equal to 1, and this if yi is equal to -1. Now, okay. So now what we can do is we can convert this maximization problem to the minimization problem. Okay. So if we convert this maximization problem to the minimization problem, what do we get? So instead of plus zi, we'll have now minus of zi. So minus of zi log of sigma of w transpose xi my plus of zi minus 1. Zi minus 1, 1 minus sigma of w transpose xi. Okay. I is varying from 1 to n. This is my function. So now, since we are all the losses that we have plotted here, we had seen it for one data point. So again, we'll stick to one data point. So if I'm just going to look at this point x comma y, then what is the loss that we are going to get for this point, right? So what is the loss for x comma y? Now you have two cases. One is when zi is equal to 1, and other is when zi is equal to 0. So we are going to first, let's look at the loss for xy if my zi is equal to 1. Okay. So if my zi is equal to 1, then I know that since this is my log likelihood, L of w, sorry, this is my log likelihood. Now, if zi is equal to 1, I know that the second term goes away. Right? So only the first term is remaining, which is minus of zi. So since we're taking zi to be 1, so we'll have minus of log of log of sigma of w transpose xi. Let's take it as this. So minus of log of sigma of w transpose xi. So the way sigma is defined, the way this logistic function is defined, it is any sigma of x is equal to 1 upon 1 plus e to the power minus x. So you can write this as minus of log minus of log 1 upon 1 plus e to the power minus w transpose xi, right? And this can be written as, so log of 1 is 0, we know. So this is going to be just log of 1 plus e to the power minus w transpose xi, because log of 1 is 0, so 0 minus this term, 0 minus log of 1 plus e to the power minus w transpose xi is just this, right? Now, if I'm saying that my zi is equal to 1, so basically what we are saying is that my yi should be 1, right? So if we try to write this term, try to add this yi also in this term, what we will have is log of 1 plus e to the power minus w transpose xi times yi. Right? It won't make any difference because my yi is just 1 when zi is equal to 1. So this can be written as this. Okay. Now what will happen if I take my zi to be 0? It means yi is equal to -1. So if we take my Zi to be 0, I know the first term goes away and we are left with the second term. And if I put Zi to be 0, I am going to be left with minus of 1 minus, I think there was a log term here, right? Log is missing. So minus of log of 1 minus sigma of W transpose Xi. So what we are left with is minus of log of 1 minus sigma of W transpose Xi, right? So this can be written as minus of log, now 1 minus and sigma of W transpose Xi is 1 divided by 1 plus e to the power minus W transpose Xi. Okay. If you solve for this, you are going to get minus of log e to the power minus W transpose Xi divided by 1 plus e to the power minus W transpose Xi. Okay. Now, what can be done here is you can divide both the numerator and denominator by e to the power minus W transpose Xi. So divide this by e to the power minus W transpose Xi, both the numerator and denominator term. So once you do it, you are going to get minus of log of 1 divided by, so you will be left with uh, this is 1 plus 1 divided by e to the power W transpose Xi, right? So this is just e to the power W transpose Xi plus 1, right? This is what you will get. Okay. And this can be written as log of 1 is again 0 and log of 1 plus e to the power W transpose Xi by I. Okay, this is fine. So log of 1 is 0, 0, 0 minus log of this. So this is fine, yeah. So you can write this. Now, let's go back to here. So we had started with Zi is equal to 0. It means we want yi to be minus 1. So if we try to introduce my yi is equal yi in this term, yi in this expression, what we can write this as? We can write this as log of 1 plus e to the power minus of W transpose Xi times yi. Now, since my yi is minus 1, so to and I know that this is just e to the power W transpose Xi. To compensate that, we have to put a minus sign here. So this is the function that we get, that is log of 1 plus e to the power minus W transpose Xi yi. Now, if you look at both these expressions, this, which is log of 1 plus e to the power minus W transpose Xi times yi, and log of 1 plus e to the power minus of W transpose Xi yi, both are same. So whether you took Zi to be 0 or whether you took Zi to be 1, we got the same expression for the loss, right? Now, this can be written as, so the objective was to minimize this term, right? Minimize this. So now I know that minus of log of sigma of W transpose Xi can be written as this, and even minus of log of this can be written as the same term. So this is basically, if I just write what is inside, it is more like minus of Zi let's call this as maybe some, because it is giving you the same expression, we can write this as maybe some zi times a plus um, or zi times log of this is going to be minus of this, right? So zi of minus of a minus of this term, which is minus of, which is plus a. So basically this all gets cancelled, and all you are left with is this term, right? So this can be written as, min over w sum over log of 1 plus e to the power minus w transpose xi times yi. I is varying from 1 to n. Okay. So in short, like um, this objective, we are able to write it in this way. Okay. This is fine. All right. So let's write it over here. So what we got is, now our goal here is to minimize over w, and we want to minimize log of 1 plus e to the power minus w transpose xi yi. Okay. And I know that this w transpose xi yi is my gx times y. Right? So we can again plot this in the same loss function that we had defined. So if we plot this in the same graph, so this is my 0, 1 loss. So this is 0, 1, and this is gx times y, and this is loss, right? So in this case, the loss that is given is log of 1 plus e to the power minus of gx times y. Okay, this is my loss. And this loss, we are calling it as a logistic loss. This loss is called as logistic loss. And it will look something like this curve. Something like this. So this loss, we are calling it as logistic loss. Okay. So again, if you see this loss, this is again a convex function, and this is also a better than what we had seen, better loss function as what we had seen in case of regression. So this also works well for the this NP hardness of the 0, 1 loss. And what were the other losses that we had seen? Let's just draw that also. So one was this one. Okay. So what we got is, we saw, like, so these can also be called as some surrogate function or surrogate losses for the 0, 1 loss, and they're all the convex function. So since the 0, 1 the 0, 1 loss was not was like, it was not easy to minimize that problem because it was a NP-hard problem. So what we saw is, we looked at this logistic loss, we looked at this SVM loss, and we saw we got different surrogate losses, and like different algorithm gave us different surrogate losses, and they were all convex. So it was like in a way, since they're convex, they can be minimized very easily, and um, we can get a minima from here. So we saw that different algorithms are giving us like how different losses are giving different algorithms are giving us different losses, and uh, based on these losses we can check the performance of all these different algorithms. So this was about the logistic and the SVM loss. Then one more loss that we are going to see here is for the perceptron. So for the perceptron, so this is the fourth one. So in perceptron, the update rule that we were using was wt plus 1 is equal to wt plus xt by t, right? This was my update rule for the perceptron problem. Now, for the perceptron problem, the loss that we are going to use is again the hinge loss that we had seen for the SVM problem, but not exactly the hinge loss that we had seen for SVM, but we'll modify it a little and we'll call it as, let's say, modified hinge loss. So we'll see the modified hinge loss. And this loss is the way it is defined is so L of W of at for any data point xy. So earlier for like hinge loss, we had defined the hinge loss as max of 0 comma 1 minus W transpose x times y. So when we are defining the hinge loss for perceptron, what we will do is we will relax this one here. So what we will say is like this is just max over 0 comma minus of W transpose x times y. This is my modified hinge loss. And now when we take the derivative, like when we try to see like how this loss vary as we change our W, then to see that, like first this was my, so how will this look like? First let's see that. So this is my gx times y, which is W transpose x times y, right? And this is how it will look like. Since we don't have 1 here anymore, so this will be centered at 1 0. Now here okay, so what we are saying here is like if we have to like if we take the derivative with respect to this loss with respect to my W, then it is going to be like now you have different conditions, like depending on what sign your W transpose x takes, W transpose x times y takes. So if your W transpose x times y is less than 0, so if this is less than 0, right, then in that case what we are going to get, like if you differentiate, so if you take dou L by dou W, right, if you differentiate this, then for W transpose x y less than 0, you have this this curve, this curve, right? Now if you differentiate this with respect to W, you are going to get only minus xy. Okay, but if you take your W transpose x times y to be greater than 0, I know that for anything greater than 0, there is no change. So no change, it means this derivative is 0 basically, right? But if we look at this W transpose X times Y to be equal to 0, if we see this for the point Y is for at exactly at 0, then in that case, I know that since this is a place where, I mean, the function is not differentiable, so of course I cannot differentiate it, right? So, but one method that we had seen, but not in detail, what we had seen is we can use to solve certain kind of this kind of problem, we can use the subgradient method, and we can get different subgradient at this point, right? We can have different subgradient, and one way if we take the derivative at this point, what we can get is like any slope between the -1 to 0 times the xy. And when we use this perceptron algorithm, it we are going to like in case the algorithm has not classified the point correctly, that is when my W transpose X Y is less than 0, then in that case the derivative, what we are going to take it as minus of xy. Okay, so if you look at this update rule for the perceptron, it looks more like the gradient descent update rule that we had seen. And what did the gradient descent update rule look like? It looked like your Wt plus 1 is equal to Wt minus some step size of eta t, derivative of grad of your f of w, right? This is what we had. But now instead of instead of this grad of fw, what we are seeing here is grad of this modified hinge loss, right? So modified hinge loss of Wt, and you are differentiating it with respect to W. This is what we have here. And this eta, and like whenever there is a mistake, we are going to, this is just going to be minus of xy. Okay. So this update rule turns out to be Wt plus 1 is equal to Wt. So instead of eta t, we'll take it as 1. We'll just take it as 1. So you will have minus of 1, and this gradient, as we saw, it's going to give you minus of xy. So you have this xy term here. Okay. So so what we're trying to basically say here is that this perceptron algorithm that we saw for this classification problem, where our goal was to linearly separate our data set, there, so you can also view your perceptron as a stochastic gradient descent method. So we'll not look at in great detail here. We just wanted to we just wanted to say here that this perceptron can be viewed as this stochastic gradient descent, where we are taking this update, this step size, this eta t, to be equal to 1. And the loss that we are using here is the modified hinge loss, and the step size is equal to 1. So that's all we are going to, that's all we are going to see for the perceptron algorithm. Like what loss do we use in case of perceptron, and it can be viewed as the stochastic gradient descent method, and we're using the modified hinge loss, and the step size is 1. That's all. Okay. And just so these have not been discussed in great detail, but the another algorithm that we saw which was boosting. And for boosting, the loss that will be used, will be e to the power minus of y of hx. And this is called the exponential loss. Okay. So the take from all these 5 examples, what I can take is like um, your original problem was an NP-hard problem, but we are able to find different surrogate convex function for different for different classification for different learning algorithms, and those are giving you a better approximation and somehow dealing with this NP hardness of the 0, 1 loss. And that's all the take from here is, because all the surrogate losses that we saw, they all are convex, and from there we can find the global minima for our problem. So that is why we have so many different classification algorithm that we have seen so far in from week 8 to 11. So depending on what surrogate function we use, we have many different algorithms, and um, we saw how this can be solved. So this was about all the surrogate function which are convex. But now we are going to go to a different algorithm where we are going to see that the surrogate function that we will define is not convex. In fact, it's not convex, but still it works quite well. And uh, that algorithm, we are going to call it as neural network. So we'll see what neural network is, and we'll see the loss that we are going to use over there. Okay. Any doubts so far? Okay. So next is neural network. All right. So here, what uh, again, the idea is still the same, that we want to solve this 0, 1 loss function, which is an NP-hard problem. And earlier, all the algorithms that we saw, we use some convex surrogate function for this loss. And for different losses, we had different algorithms, and we saw how all these algorithm works. But now this we are going to go into this another algorithm, which is neural network, and it uses and it is more like the extension, or you can say maybe uh, yeah, extension of the perceptron algorithm, or it has come from the perceptron algorithm. So like remember, like when we were talking about the perceptron, we had again the data set which were in some d dimension, and the output that we were getting from the perceptron, where we were learning some w, and then we were going to look at sign of my w transpose x, and then we were classifying a data point as +1 or -1. This was the framework for the perceptron algorithm. So when we look at it pictorially, so we have my data set, which is an RD. And how did this data set look like? So my data set, this X is X1, X2, so on till XT. It was in D dimension, right? And my output, we were learning W, and we were looking at sine of W transpose X. And this was my output, right? So the way we can view this pictorially is we can take, we have all these input as X1, X2 is all these features, X1, X2 up to XT. So these are input features. Now, these are my input. Now all these are given a weight, which is W1, W2. So you have a W1, you have W2, and then so on till WD, right? And then you get a final output. So these were the weight associated with your data, all the features. And then you get an output, which is nothing but W transpose X. Just the linear combination of your data point, right? Sorry, linear combination of your weight and data point. So this is our output, which is W transpose X. So our goal was to learn such W that best explain your Y, right? So we are going to now extend this idea, and like instead of like here we have just one W that we are learning in perceptron, right? Here we are just learning one W. But in neural network, what we are going to learn is not just one W. We are going to learn many Ws and see how this is how the neural network will work. Okay. So in neural network, now my input layer is, so I look at my input layer. So again, I have my X1, X2, X1, X2, so on till XD. Now, all these Xi's have some weight associated with them. So there is, you can have many hidden layers over here, but a very very simple neural network that we're going to talk about is with one hidden layer. So let's talk about this. So hidden layer, you can have maybe some K neurons over here. So let's say you have one, two, let's say some K neurons. And each exercise will go to one neuron. So you have X1 goes to the first one, and the weight that is associated with this is, let's say, W1 for the first. Now, X1, sorry. Now, if I talk about X2, so X2 can go to 1, and this will have the weight associated with it as W2 for 1, right? So on for all the data points. And if I talk about XT, so this will have the weight D, and this subscript 1 denote which neuron I am feeding this weight as for each of the data point. Now the same you can do for all the neurons over here, since what we're saying is in our hidden layer we have, let's say, some K neurons. So my first neuron can also go to the second one, and the weight associated for this data point to the second neuron, let's take this as W1 and the superscript 2. Then for X2, we can take this as W2 of 2, and for XT you can have this WD of 2, right? Similarly, you can do it for the kth one. So This will go here, this will go here, and this will go here. So the weight associated with this will be WD for the kth neuron, right? So these are the weights that you have for different data points and different weight associated with different neurons that you have. Now this is the hidden layer that we are calling this layer as the hidden layer. So what is happening in each of these neurons is like once all these weights are coming from all these data point, so this first neuron will give you W of 1 transpose X, same as what you were getting from the perceptron algorithm, right? Like there you just wanted to learn just one W, which best explains your yi's, which best explains your y. But here you have some k different w's that you want to learn, right? So for different neurons, you are going to get, so you will get w2 transpose x, from so on till you will get w k transpose x. Okay, so this is what is happening inside the hidden layer. But apart from this, what is happening is that all this output, this W1 transpose X, W2 transpose X, all this is passing through the activation function. So this activation function is trying to bring the it's a non-linear function and is trying to bring the non-linearity in the features. Okay, so this activation function is what we are denoting it as A, and we'll see what are different activation function are there. So what will happen is like every output that you see inside this hidden layer, so that will pass through this activation function, and this will become so when this activation function acts here, so it will become W1 transpose X, A of W2 transpose X, so on till A of WK transpose X. Okay, now all these activation function, now combining everything you have, once you combine everything, you get the final output. So this is called the output layer. Okay, and for each of these A of WK transpose X, you have some weight associated with each of these in the output layer. So in the output layer, you have the weights for all of each of these inputs. Now you're getting is W1 out. For the second one, let's say W2 out. So out is just representing your output. Then WK out. All right. So once everything goes in the output layer, the final output that you get is W of out transpose, W transpose, your A of W1 transpose X, so on till A of W, this is WK transpose X. So this is the final output. So again, okay, so what we have seen here is the simplest neural network that can happen, but it is quite possible that you may have many hidden layers inside. This is just one hidden layer. We can call it as layer 1, but you can have many different layers over here inside. And we are going to see like what activation function we can use for over here, right? So there are the activation function that we are going to see in this course. I mean, neural network we are not going to see much in this course, but this is just a short introduction of what neural network is and what it does. But in more detail, you will see only in the courses like deep learning. So this is just a starting for maybe you can think of it as prerequisite or something. So one activation function that is introduced is let's define it as you have said to be 1 upon 1 plus e to the power minus z. So this is a sigmoid function, and I know this is a differentiable function, um, and this how does this look like? So if we plot this sigmoid function, it lies between 0 to 1 and looks something like an S. No? Yeah, something like this. So this was your sigmoid function, and uh, this um, this function can is used quite vastly, like for bringing the non-linearity in the features. And the other activation function that you're going to look at is something called ReLU function, and that is defined at just max of 0 comma z. So how can this be seen as? So this is just, so if z is less than 0, this is a 0, otherwise this, right? So this is how this function looks like. So these are two activation function that is being defined. And now let's say if we have to solve some regression problem from this neural network, then what output do we expect? So the output that we'll expect from here will be, so W hat, right? So W hat is just going to be sum over your Wi um, out, right? And this function. And this is what? This is just A of Wi transpose X, where I is varying from 1 to n. This is okay. This output. Okay. So the parameters that needs to be specified in the neural networks are these parameters. So you need to know all these WIs. So you need to know all these W1, W2, and so on. So you have W1, W2, so on till WK. You need to know all these Ws. And you should also know this W out, right? You should know all these weights. So W out. So these are the parameters that need to be specified for this neural network. Once we know, we can solve this problem. And how many layers that we want, that also need to be specified a priori into the model. So this is the design for the neural network. Now, okay. So after this, we're just going to look at like what loss function that can be used um, here. So if we look at the regression loss, so if we look at the regression loss, so in regression, the loss we had defined it as the squared sum of squared loss. So the same can be done here, like for this regression problem. If you want to solve the regression problem, so the loss of this neural network, so the loss of this neural network for any xi with respect to the parameters theta, where my parameters are all these weights, comma this wi. So this can be given as what is forward pass and what is backward pass. You don't have to know right now. Like this is a very basic. In this course, you're just going to look at a very short intro to the neural network. All these will be done in your deep learning course. So all this back propagation, CNN, RNA, you'll see later. So just the design of the neural network is what is important to you right now. So okay, so the loss of this neural network. So if you look at the regression loss, we're just going to this model xi comma theta minus of this yi cos square is what we will take, right? This is the loss, regression loss that we have. Now, okay. I don't think there is anything more that we should discuss here. Okay, this was a very this is very simplest neural network that is being given here, but you can also have many layers inside this, many layers inside this hidden layer, and we are not going to look at it in this course, so we can stop uh, at this topic right now. So this was all about this was all major topics that you had in week 12.
Hello, ma'am.
Yes, Faz.
Actually, how do we know that when we have to use a rectified linear unit and sigmoid function?
Yeah, that also is not required right now.
Okay.
So like how do you learn these W's has not been done in this course, so you don't have to know right now.
Actually, I saw Karthik sir notes, that's what I'm saying.
Okay,
And also,
so
and
so
also in PY, also in some PYQs, I saw the question related to ReLU and sigmoid function.
uh, is it? I mean, these activation function has been defined, but how these functions are, like in what cases, like how do you learn these W's and when do you use these functions?
So,
They
ma'am,
have not been discussed.
in a PYQs, questions from these topics are given.
Okay. So what kind of questions are there?
That there was given one data set and said that what you have to use here, ReLU or sigmoid function, and cross entropy also.
Cross entropy.
Yes, ma'am. In a cross entropy, we have to use sigmoid activation function.
Sigmoid activation function. Okay, those have been asked in the exam, is it?
Yeah, ma'am, asked. In PYQs, I saw this.
Okay, okay. So, okay. So like what we saw is just is like when we are doing the regression, like in case we are solving the regression problem, but if we are using, if we are looking at the classification loss, then in that case, the only thing that will change, everything is same, the whole setup is same. The only thing that will change here is you have all these data point, this x1, x2 up to xd, and you have, let's suppose you have many hidden layers. Okay, so let's say the layer 1 you have some neurons, layer 2 you have some neurons. They need not be equal numbers. It may different. You may have many layers, maybe let's say some m layers you have, and for everything you have like you will have the weights associated with all the data point to all the neurons, right? And the final input that will go to your output layer, this we are talking from the perspective of the when we are using the classification laws. Okay, so the final output that you will have, so everything will go here. uh, this will be the output will be sigma of w of out transpose of all the inputs that you have. So the inputs will be of all the weights time all these data points. So we can just write maybe some I or inputs. Okay, so this is the output uh, that we are going to get, and this sigma is basically your sigmoid function that we had seen, this one, 1 upon 1 divided by 1 plus e to the power minus z. And to, to work with this classification laws, we can use something called the cross entropy laws. And again, not much has been discussed here, so I can just there's no point going into detail here. So what you do is you use the cross entropy laws. So like whenever you have this like whenever you have this sigmoid function coming into the picture. What is the most appropriate choice of activation function for the output layer if the binary cross entropy loss is used? Yeah, so sigmoid is better here, right? Relu definitely no. Okay.
Yes, ma'am. Sigma would be answer.
Mhm. So you don't have to go into details. So just stick to like whatever sir has covered. No, just stick to that much for now.
Okay.
Do not anything in detail about neural network you will study in the further courses. Okay.
Can I share my screen for one question?
Okay. Hold on, I will stop presenting. Okay, so we can. I'll just stop this.